Welcome back, everyone. In the previous lecture, we were talking about the various oil and various properties that are needed for the oil and gas pipelines. So we ended up with the pour point in the last lecture, and in this lecture, we will talk about the vapor pressure. Well, it's a very important parameter for physical parameter. It is important for the oil pipelines as well as for the oil tankers, because in summer, when these vapors evaporate and come out of the oil, they can create a lot of pressure, and which can cause, sometimes even the blast. So we have to look at it carefully. What is this vapor pressure? And we make sure that we maintain the pressure above this one so that nothing happens here. So first of all, we have to understand what is vapor pressure. In order to understand it, let's look at the simple container, and let's look at it, what's going on. Take an example of cola or something. Then let's take this example. Imagine that this is filled up with oil, and if the upper part of this one is bit empty, here this part is empty and here is full with water. Now once you shake this container here, actually once you shake this container here, there are small particles, there are very small particles uh, can evaporate here, here. The very small, they will be like a gas. You cannot see them actually, but there are very small, tiny particles that are accumulated here. Now, these small and tiny particles actually together creates a pressure at the surface here, and that is called the vapor pressure. So, pressure caused by these small droplets, vapors, which came out of the water or oil or whatever it has. So this vapor pressure is a big problem, and I will show you in a video that how this can be a disaster for oil and gas pipeline. So
results of what happens when you start studying intermolecular forces and we start making a little bit more of a condensed phase such as solids and liquids, you start getting all these unique properties of solids and liquids. Liquids have quite a few unique ones: viscosity, surface tension, and one of the more unique ones is vapor pressure. That's a very special case, and that's probably another thing completely. So let's just think about it. If you take water in a container and you allow it to start evaporating, the space above the surface of the water will start getting water molecules. That means it's a gas now, and gases impart pressures. So as that builds up, what's going to happen is these particles floating above the water can go back into the water unless they're whisked away. So if you put a lid on the container, all the particles are trapped, so the water starts going back into the water phase, or I should say the water vapor goes back in. As this happens, you finally reach a state at which the exiting evaporation rate equals the entering condensation rate, and you reach what we call equilibrium. So when those two rates equal, you establish a constant pressure inside your container, and that pressure is called the vapor pressure of that liquid. In the case of water, you would say it's the vapor pressure of water. It's an example of what we call dynamic equilibrium, meaning when you look at the thing, you can't tell anything's happening, but in actuality, there are billions and billions of molecules leaving the surface of the water, and there's also billions and billions re-entering, and they are exactly the same rate. So there's no net change, but you have established what we call a vapor pressure. And that's hopefully a little bit more of a handle for you on what vapor pressure is. We have other things to tell you later about vapor pressure in other videos.
When a tank is exposed to sustained heat, such as from a fire, the liquid within the tank is forced to boil or vaporize, resulting in increased pressure in the tank. To prevent overstressing the tank, the relief device activates, venting the excess pressure. As pressure decreases in the tank, the valve begins to close. With continued heating, pressure again builds, causing the relief valve to reopen. flames impinge on the tank below the liquid level, the liquid absorbs the heat, allowing the tank metal to remain at a safe temperature. With continued relief valve operation, the liquid level drops, exposing a greater area of the tank to the effects of heating. With the flames impinging on the vapor space of the tank, the temperature of the tank metal, uncooled by liquid, rises. At some point, due to the vapor pressure from within, the tank metal begins to weaken, stretch, and eventually tear. As the tank comes apart, large quantities of both liquid and vapor are released in a powerful explosion. The heat radiated is sufficient to ignite combustibles and cause burns great distances from the explosion. Tank sections containing rapidly igniting fuel can become flying missiles, traveling great distances, causing secondary fires and other damage. It all happens quickly and with little warning.
Let's go ahead with the, so this is the, and then we have a true vapor pressure, and it's a common measurement of the volatility of petroleum distillate, like how much vapors can come out, and you can measure them using the ASTM method D2879. This is the American standard testing methods that we can measure them. Now after that, this at normal conditions the crude oil is fine, but if you have the lighter hydrocarbons like LPG or the methane, ethane, propane, butane, they can vaporize and can create problems in the pipeline. So when we operating at pressure should be higher than their vapor pressure, so that there should be no separation and should not be a blast in this case. Then we have the flash point. It's a minimum point at minimum temperature at which the temperature the oil can ignite. For example, in summer, sometimes in some places temperature goes above 55. So there are some crude oil they can catch fire at it. So it's a minimum temperature at which it can catch fire. Or there are many petroleum products that can catch fire because they are highly flammable at the same time. So we look at it, and I will show you now the video of the flash point, how it actually is happening.
For this test, you're going to need some basic equipment. A metal tin or can, a big bean tin is fine. A piece of plywood or something similar to put the flame out at the end of the test. A digital thermometer, and a gas blowtorch of the sort that plumbers use. And of course, a sample of the fuel you want to test. Half fill the can with the fuel sample. Once you've finished that, put the cap back on and move the sample well away from the test site. Put the thermometer into the fuel. As you can see, it's at roughly room temperature, 20 degrees at the moment, and pass the flame over the top of the can 2 or 3 times slowly. Nothing happened, so put your thermometer into the fuel and use the gas flame to gently heat the sample up. You want it to rise about 5 degrees. So you can see we're at 25 degrees centigrade now. Remove the thermometer and again pass the flame over the top of the can. Nothing happened, so go back to heating. Heat it up another 5 degrees. When you're doing this, when you're passing the flame over the can, pass it over slowly enough that it touches the surface of the fuel, but not so slowly that it begins to heat the fuel. It's a bit of a knack. You've got to keep trying it and get it right. So now we've got to 30 degrees. We've tried it. It still hasn't flashed, but being kerosene, it probably will soon. So we'll heat it up, this time to 35 degrees. Now, as you can see, there was a flicker of flame this time. It can't sustain a flame, but it does try to flash. So now we're going to 40 degrees. 40 degrees centigrade should be the flash point of kerosene. And yes, you can see it has caught fire. Now, before it gets out of control or heats up too dangerously, place your piece of plywood over the tin and put out the fire.
Flash, it can catch a fire. That's why the flash point is important whenever we are transporting the the crude oil through the pipelines. Then another the property which is important is the heat capacity of the liquid. As the amount of heat required to increase the temperature of a unit quantity of a liquid by a specific amount. So heat quantity also is important. At the same time, thermal conductivity. For example, if the weather outside is 55, how much the heat can be transferred to the pipeline and to the oil. So these heat capacity and heat thermal conductivity, they are interrelated. And if the temperature is raised because of the weather outside, it can really change the volume, it can change the pressure and so on. So these are the properties. When we talk about the oil and gas pipeline, we have to be careful for these properties. And now after this finishing this chapter, we will solve some mathematical questions to find out the pressure requirements for the pipeline. So stay tuned and see you in the next lecture.